Study with Artemis, Inc. podcast. This information was produced with the assistance of AI-generated content. Archaeological Methodologies, a comprehensive overview. Welcome to this discussion on archaeological methodologies. Today, we'll delve into the diverse techniques and approaches archaeologists employ to uncover, interpret, and preserve the human past. Archaeology is far more than just digging. It's a systematic, scientific discipline that relies on a robust set of methods to reconstruct ancient societies, understand human behavior, and trace cultural evolution. Our journey begins with the very first step in any archaeological endeavor: survey. Before a single shovel touches the ground, archaeologists must locate potential sites. This is a crucial phase, as it helps define the scope of future investigations and ensures that resources are allocated effectively. Archaeological survey can take many forms. One of the most common is the pedestrian survey, also known as a field walk. Here, teams systematically walk across a landscape, often in transects, looking for surface indicators of past human activity. This might include pottery sherds, stone tools, building foundations, or even subtle changes in vegetation that suggest buried features. The goal is to identify concentrations of artifacts or features that could indicate a site. Beyond walking, technology plays a significant role. Geophysical survey methods allow archaeologists to see beneath the ground without disturbing it. Techniques like ground-penetrating radar, GPR, magnetometry, and electrical resistivity can detect buried walls, ditches, hearths, and other features by measuring anomalies in the Earth's magnetic field, electrical conductivity, or radar reflections. These non-invasive methods provide invaluable insights into site layout and complexity before excavation begins. Aerial photography and remote sensing offer another powerful perspective. From airplanes or drones, archaeologists can identify crop marks, soil marks, and subtle topographic variations that reveal ancient field systems, settlements, or burial mounds invisible from the ground. LiDAR, light detection and ranging, is a particularly revolutionary remote sensing technique that can penetrate dense foliage to map ground surfaces and reveal hidden archaeological features with incredible precision. Once potential sites are identified and mapped through survey, the next critical phase is excavation. This is perhaps what most people associate with archaeology, but it's a highly controlled and destructive process. Every layer removed, every artifact taken, is a permanent alteration of the site. Therefore, meticulous recording is paramount. Excavation involves the systematic removal of soil layers, or strata, to expose archaeological remains. The principle of stratigraphy is fundamental here. In an undisturbed sequence, the deepest layers are the oldest, and the layers above them are progressively younger. Archaeologists carefully record the depth, composition, and contents of each stratum, creating a detailed three-dimensional record of the site. This contextual information, where an artifact is found in relation to other artifacts and features, is often more important than the artifact itself. There are different approaches to excavation. Horizontal excavation, also known as area excavation, aims to expose large areas of a site to understand the spatial relationships between features, such as houses, workshops, and activity areas within a settlement. This is crucial for reconstructing daily life and community organization. In contrast, vertical excavation, or test pitting/trenching, focuses on digging deep, narrow cuts to understand the chronological sequence of occupation at a site. This provides a stratigraphic profile, revealing how the site developed over time. Often, a combination of both horizontal and vertical methods is employed to gain a comprehensive understanding. As artifacts and ecofacts, environmental remains like seeds, pollen, or animal bones, are uncovered, they are carefully documented, photographed, and bagged with precise provenience information. This detailed record-keeping is essential for all subsequent analysis. Moving beyond the act of digging, one of the most challenging and crucial aspects of archaeology is dating. Determining the age of archaeological remains allows us to place sites and events within a chronological framework. Dating methods are broadly categorized into two types: relative and absolute. Relative dating methods establish a chronological sequence without providing a specific calendar date. Stratigraphy, as mentioned, is a primary relative dating technique. Deeper layers are generally older. Another method is seriation, which orders artifacts or assemblages into a chronological sequence based on changes in their stylistic attributes or frequency over time. For example, pottery styles often evolve, and by observing these changes, archaeologists can create a relative timeline. Absolute dating methods, on the other hand, provide a specific calendar date or a range of dates. The most widely known is radiocarbon dating, carbon-14. This method measures the decay of the radioactive isotope carbon-14 in organic materials, like wood, charcoal, bone, or textiles, up to about 50,000 years old. By comparing the remaining carbon-14 to known decay rates, an approximate date can be calculated. Dendrochronology, or tree ring dating, is another highly precise absolute dating method. By matching the unique patterns of tree ring growth in archaeological wood samples to master chronologies of known age, archaeologists can pinpoint the exact year a tree was cut. This method is limited to regions with well-preserved wood and established master chronologies. Other absolute dating techniques include potassium-argon dating for very old volcanic rocks, useful for early human sites, thermoluminescence for ceramics and burnt flint, and optically stimulated luminescence (OSL) for dating sediments. The choice of dating method depends on the material available and the age range being investigated. Once artifacts and data are recovered from the field, the work moves into the laboratory for post-excavation analysis. This phase is often more time-consuming than the excavation itself and is where the raw data truly begins to yield its secrets. Artifact analysis involves cleaning, conserving, classifying, and studying the vast array of objects recovered. This includes pottery, stone tools, metal objects, glass, and more. Specialists examine manufacturing techniques, materials, function, and decorative styles to understand technology, trade networks, and cultural practices. For instance, analyzing pottery can reveal dietary habits if residues are present, or trade routes based on clay composition. Ecofact analysis focuses on environmental remains. Zooarchaeologists study animal bones to understand ancient diets, hunting practices, animal domestication, and environmental conditions. Paleobotanists analyze plant remains, seeds, pollen, charcoal, to reconstruct ancient environments, agricultural practices, and diet. These studies provide crucial context for human interaction with their environment. Human remains analysis falls under bioarchaeology. Skeletal remains can reveal information about age, gender, health, diet, disease, trauma, and even migration patterns of ancient populations. This field provides direct insights into the lives and health of past individuals. Material science analysis employs techniques like X-ray fluorescence, XRF, neutron activation analysis, NAA, and petrography to determine the chemical composition and source of raw materials, helping to trace trade routes and resource procurement strategies. Finally, all this data is synthesized and interpreted. Data interpretation involves integrating findings from all analyses to construct a coherent narrative of the past. This often involves statistical analysis, spatial analysis using geographic information systems, GIS, and comparative studies with other archaeological sites or ethnographic data. The goal is to move beyond simply describing what was found to explaining why things were as they were. Throughout all these methodologies, ethical considerations are paramount. Archaeologists have a responsibility to preserve the archaeological record for future generations, respect cultural heritage, and engage with descendant communities. This includes responsible stewardship of sites, proper conservation of artifacts, and careful consideration of the impact of archaeological work on local populations and indigenous groups. Repatriation of human remains and sacred objects is a significant ethical issue in contemporary archaeology. In conclusion, archaeological methodologies are a dynamic and evolving set of tools. From non-invasive surveys to meticulous excavation, precise dating, and in-depth laboratory analysis, each step builds upon the last, contributing to a holistic understanding of human history. It's an iterative process, where new discoveries often lead to new questions, driving further research and refining our understanding of the complex tapestry of the past. Thank you for joining this overview of archaeological methodologies. Copyright 2025. Illustrative references. Bond, P. and Renfrew, C. 2016. Archaeology, Theories, Methods and Practice, 7th edition. Thames and Hudson. Harris, E. C. 1989. Principles of Archaeological Stratigraphy, 2nd edition. Academic Press. Kwame, K. L. 2006. Geophysical Surveys as Tools for Archaeological Site Evaluation. in Remote Sensing in Archaeology, pages 165 to 191. Springer, Boston, Massachusetts. Vitelli, K. D., and King, C. 2006. Archaeological Ethics. Altamira Press. Taylor, R. E., and Aitken, M. J. 1997. Chronometric Dating in Archaeology. Plenum Press.